I think the board is visible.
Yes, sir.
Okay, so in the last class, we discussed different components of DC machine, the construction of DC machine by a figure. And then we discussed the operation of a DC generator and specifically how the alternating voltage which we get induced in the coil, the alternating voltage which is getting induced in the coil, how it is rectified, okay, by the use of brass and commutator arrangement. As we need at the terminal, at the output terminal of the DC machine, we need only a DC. So therefore, we have to rectify the waveform. I'm not audible. I'm not
Yes, sir.
audible. I'm audible or not?
Yeah, yes, sir, you're audible.
But somebody is writing that I'm not audible. Okay, so let's check. Swastik Anjilal is saying that sir, you are not audible. I don't know. Then you check if I'm clearly audible to rest of. Uh, then you have to check Swastik. You have to check your audio device, your speaker properly. Now that we discussed, so how the induced EMF, which is alternating in nature, how that is converted to a full wave rectified one by the use of brass commutator arrangement. So we discussed in details how we get a unidirectional voltage out of this bidirectional voltage. And that arrangement is called brass and commutator arrangement. And somebody asked me that if we need the same alternating voltage at the output, if we don't need any DC output, unidirectional output, if we need only bidirectional output, that means the same alternating voltage waveform, if we want to have outside, then what should be the arrangement? So I discussed that another arrangement is there that is called the slip ring and brush arrangement, by which we can get the same alternating voltage at the output. Okay, so by using two slip rings, because you need two polarities, so you have to use two slip rings for that. By using that, you can get same alternating voltage at the output. Not only that, if you want to provide alternating voltage waveform in the coil, then also you can apply your alternating voltage at the output, and by the slip ring, you can provide that in the coil. Now, let me know, that means you just tell me that if we want to apply a DC in the coil, and we also want DC should flow in the coil, so what should be the arrangement? Can anybody tell me that we need DC current to flow through the coil, and we have also at the output, at the input terminal also we have DC. So what should be the arrangement? Is my question clear? Anybody?
Sir, is it brass commutator arrangement?
Why? Okay, so you are saying brass commutator
Sir,
arrangement. Hmm.
sir, at output we will get DC. No, so input will be always DC because we are changing the polarity changes after each rotations.
No, no. My question is, I want DC current to flow through the coil, and as input also I have DC voltage. So what should be the arrangement by which we can flow a DC current through the coil if I have DC voltage as an input? Okay. Anybody else? Okay. So that then I will discuss that later. If you Nirmala Nandi has written that slip ring arrangement. Okay, so why slip ring arrangement? Can you explain? Nirmala Nandi, why the slip ring arrangement is required? Nirmala Nandi, are you there? Inside in front of the device? Okay. Anybody else?
So, so because that every time A will remain the same polarity for slip ring arrangement.
Hmm. And
And so the direction of the current flowing in the coil will always be the same, means a kind of a direct
that means
DC
what we
current.
need? What kind of arrangement we need? Just
Slip ring. Then
slip ring. That means
it's a
brass
slip
commutator
ring.
is wrong answer. You were telling that. You were saying that.
Yes, sir. Yes, sir.
Okay.
Yes, yes.
So that means if we don't need any conversion of AC to DC or DC to AC, then we have to use the slip ring arrangement. Now, in the last class, we discussed if we don't need any conversion of the voltage waveform, that
Sir,
is,
you told that all throughout the thing will be DC.
yeah.
And the question that you asked, in that question you told that the input will also be DC, the output will also be DC, and the current flowing through the coil will also be DC.
No, 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 no. My question is not exactly related to the DC machine. I'm asking that suppose I have a DC voltage and I want that the DC current would flow through the coil. So what kind of arrangement should we make?
Okay, means that we have DC in the coil, we have to get the output also DC without any
No,
conversion.
not the output. Here the thing is opposite. Okay, so therefore it may not be a generator. Try to understand. In
Yes,
case
sir,
of
but
motor,
when we are inducing the in the first class you told that when we are inducing the flux, the d phi dt, it can never be constant in that case, because the flux
uh,
itself, when we are calculating the voltage
uh,
induced, it will be
uh,
varying with time. Then
uh,
how can it be DC
I'm not getting you.
in the coil?
Actually, I don't want the output, voltage output. My objective is to flow the DC current through the coil only. I don't need any output voltage. I have the output voltage with me. Suppose I have a battery. Suppose I have a battery. Okay, so
Okay,
battery
sir.
is a DC voltage source. And what I want to flow the DC current through the coil. Are you getting now?
Okay, sir. Okay, sir.
Now,
So
you are
actually,
confused.
my question is which coil? field coil or the armature?
Armature coil. Because otherwise you don't need any such arrangement. So slip ring and brass commutator arrangement is required only if you are interacting with a rotating coil.
Yes, sir. That is only I am telling that how can we
If a
produce
static coil
DC
is
in the
there,
armature coil? How can we produce DC in the armature coil? Because armature coil is
we are
because
not
you
producing DC. We are giving DC. We are supplying DC. We are not producing
okay,
anything.
we are not producing, but the link is through magnetic field. So we
No,
are
no, no, no.
actually
The link is brass through the brush only. Through the brush only. The link is through the brush.
okay. It's the other way around. Okay.
Are you getting now? Okay.
Okay, sir. Means it's the other way around. We are supplying through the brush. Okay, sir. I thought we were when extracting through the brush. Okay, sir.
We are not extracting. We are not developing anything.
Okay, sir. Okay. This is a motor. Okay.
Okay. Somebody is saying that
I was thinking of a generator.
Connection is very poor quality. Okay. Okay, no problem. Actually, that also sometimes we need. What we have just asking you. Suppose sometime we need here in a DC machine. You see here in a DC machine, our the magnetic poles are fixed, isn't it? And sometimes some magnetic poles we need which will rotate. So suppose this is a magnet. Okay, now we can rotate it like this, isn't it? This is a permanent magnet. It's a north pole, it's a south pole. Now we can rotate it. Then the north pole and south pole will rotate. And suppose you have some coil wound here. Then the same thing you will have in the static coil. So then that means same DC machine we can also think of. Suppose if we rotate the magnet, and suppose if we have the armature coil in the stator, then also the similar thing you will get. But the problem will be there. Your your brass commutator will not be required for the stator, and it will not be helpful for also the stator, isn't it? Because in the stator you will get the alternating voltage. Then by some other arrangement you have to rectify the voltage. Am I clear? So these are
Sir, please repeat this again.
I am just telling you that suppose this arrangement I have drawn. Forget about the basic decimation. This arrangement I have drawn. I have the permanent magnet, north pole and south pole. So if I rotate this, and if I have armature coil in the stator, okay, so what is the voltage induced here? What type of voltage will be induced here? Suppose this is the AB coil.
Alternating.
This is alternating voltage. So that means you will get an alternating voltage VAB. VAB will be AC, isn't it? Are you getting?
Yes.
And if we want to make it, suppose I want to make a different DC machine, not DC machine in our book. So this is how another arrangement we can make a DC machine. It's very simple. If we have a magnet, if we rotate that, and if I have a coil like this in the stator, so it's very easy to have alternating voltage at least, because again I am just telling the same thing that DC voltage cannot be induced. Only AC voltage can be induced or developed.
Yes.
Now, if we have some solid state rectifier, like bridge rectifier, okay. So if we have solid state rectifier, diode rectifier, like that, then what can we have? We have DC. So this is how another DC machine we can another DC machine we can make. We can develop. Why not?
Sir, in this case, we cannot use the brush commutator system.
We cannot use, not only that, we don't
The brass.
require also. We don't require also. Now the question is, in this type of machine that I have just drawn, here we need a permanent magnet. But think, if we don't have permanent magnet, if we have a iron core, how can I make it a field? By a field coil. So where should I provide the field coil?
Yes.
That is my question. So I have to provide here only because here the rotor is my field. Here this is my field. Just a minute. This is my field and this is my armature. So this is my field and this is my armature. So here our field is rotating, but armature is static. This can be another possibility where your field is static and armature is rotating. Then also you can arrange some DC voltage out of it. But if the field is permanent magnet, then it is okay. Then if the field is not a permanent magnet, if it is an electromagnet, so how can I get the electromagnet? Because it's a rotating. And electromagnet, how we can make? If we have some DC voltage, like battery, and we have to give the supply to this, then it will be an electromagnet, isn't it? Then my question is, what should be the arrangement so that I can create a north pole and south pole in the rotor? Again, you have to make some arrangement between the static and rotating thing, because your DC supply, this is static. Your DC supply is static. So this is the supply for your field. Are you getting? আমি কি বলছি বুঝতে পারছো? This is a supply for your field and that is static. But the field, actual field coil, field will be rotating. That means the field coil will be also rotating. So what should be the arrangement by which we can give this DC supply to this field so that I can have some fixed north pole and fixed south pole?
So slip
Slip
ring
ring, sir.
arrangement.
Slip ring.
Correct. So that means again we need the slip ring arrangement, not the brush commutator arrangement, because here we don't need any conversion. So therefore we need slip ring. Are you getting? We don't need any conversion. We have DC at the static terminal and same DC we want as a current flowing through the field coil so that we can generate a fixed north pole and fixed south pole. So for that we need only the slip ring arrangement. So that means this DC machine will have slip ring, not brass commutator. Brass commutator is required for rotating armature construction. Are you getting? Anyway. So exactly this type of DC machine is not there in market, but still I am just discussing. But a variation of this will be available in market in form of either form of PMDC or brushless DC motor, BLDC. Not generator, but as a motor, this type of constructions are also available, where the field system is rotating, but the armature is static. So either it is called the permanent magnet DC machine or brushless DC machine. Okay. So I think you have understood where we should use slip ring and where we should use brush and commutator arrangement.
So in this case, if we provided a AC field supply, then in that case, we would not have to rotate the electromagnet.
Hmm? Then it will
So
be
if we sorry, sir.
then it will be a transformer. if we have alternating supply in
Oh,
the
okay, okay.
inner component and outer component also, if we want the AC voltage, then it will be just converting uh, same AC to AC. That means it will be a transformer. It will not be a DC machine.
Okay, yes, sir.
There you don't
Yeah.
need any mechanical rotation, so it will not convert your mechanical power to electrical power or electrical power to mechanical power. That means that
Okay.
machine will be no longer a rotating machine or electrical machine. It will be a transformer. Is that clear?
Okay, sir. Yes, sir.
Okay. So next, then we discussed the basic relation between electrical angle and mechanical angle. Okay, so before that, what we discussed in that class, how we get in a normal DC machine, how we get almost a ripple-free DC, how we can get. So for that, what we do, we make our winding distributed along the armature periphery. So this type of winding is called the distributed winding. You see, they are distributed. One coil is there in A prime, another coil is there in B prime. Not all the coils are at the wound and at the same angular position. They are distributed along the angular positions along the periphery of the armature. So this type of coil is called the distributed coil. So the advantage of the distributed coil is we'll get the induced voltage with some lag, with some phase angle. And that phase angle, which is called gamma, is called the angular slot pitch, is basically the angle between two consecutive slots. Okay, so though it is a space angle, this gamma, as you can measure by the geometry, it is basically a space angle. The angle in space. The A slot and B slots are different in space. So basically the gamma is the space angle. But you see where I am drawing the voltage, then it becomes the time angle gamma. Here it is the time angle. Here it is no longer a space angle. Here it is a time angle because it is measured in time. Anyway, so that is the advantage of using the distributed coil. We get the induced voltages with different phase angles. And if we sum up all this rectified component of coil contribution, then the ultimate voltage which we'll get is almost ripple free. Okay, so that is the advantage. So that kind of filtration we can perform using distributed coils in a DC machine. And the end we discussed in the last class that what is the difference between the mechanical angle and electrical angle? So all the angles you have measured so far is mechanical angle. From your school days, whatever angle you have measured in mechanical angles. Okay. So suppose in a closed circular, how much angle you will get? You will get only 360 degree. If you rotate twice, then you will get 720 degree. But if you rotate once, then you will complete 360 degree only. But if we have number of poles more than 2, then we can also get more than 360 degree in one complete revolution. Okay, so that creates the difference between the mechanical angle and electrical angle. একবার যদি আমি ঘুরে আসি সার্কুলার পাথে, তাহলে অ্যাঙ্গেল চেঞ্জ হয় 360 ডিগ্রি, এটা আমরা সবাই জানি। কিন্তু লাস্ট দিন আমরা দেখেছি যে এক পাক যদি ঘুরে আসি, তাহলে ইলেকট্রিক্যালি আমরা 360 ডিগ্রির চেয়েও বেশি অ্যাঙ্গেল ঘুরে আসতে পারি যদি নাম্বার অফ পোলস হয় মোর দ্যান 2। Okay, and the relation we established in the last class, that electrical angle equals to P by 2 into mechanical angle. So that means this conversion totally depends on the number of pole. And the number of pole, if it is 2, then there will be no difference between the electrical angle and mechanical angle. Remember, if the number of pole is 2, then there will be no difference between the mechanical angle and electrical angle. If we revolve once, then we'll complete 360-degree mechanically and also electrically if the number of pole is 2. But if the number of pole is 4, then in a complete revolution, we'll complete 720 electrical degree. Is that clear? Now you see, so that means if we complete the electrical revolution 360-degree, a complete revolution of electrical 360-degree. What is the mechanical revolution? Mechanical 360-degree will be there. So this is one complete revolution, isn't it? Okay, so one revolution. But electrically we don't say revolution. What we say? Do we say revolution in electrical? We say one cycle. One cycle is completed. But mechanically we can also say revolution. Okay. And this part time, one cycle per second. And this is revolution per second. Will give me this relation F equals to P by 2 into N. Okay. So this is called the revolution per second, RPS. And one cycle per second, it is nothing but the frequency. So frequency has the unit of cycles per second. And now this is the old unit of frequency. Now the unit of frequency becomes.
So we cannot hear you clearly.
Huh?
So we cannot hear you clearly. Sometimes the volume is reducing.
Acha, it is breaking or reducing, attenuating.
Yes, sir.
Reducing. So reducing.
Now it is okay.
Yes, sir.
No, I'm just telling you that how we are getting this formula. F equals to Pn by 2 that we have already used in our earlier expressions. Electrical angle equals to P by 2 into mechanical angle. So that means 360 electrical angle equals to P by 2 into 360 mechanical angle, isn't it? So one complete cycle in electrical, that means nothing but 360 degree, and one complete revolution in mechanical, that is mechanical 360 degree. Okay, so then I have divided both sides by the second. Then we'll get 1 cycles per second equals to P by 2 into 1 revolution per second. That is N. Now it is clear. Is that clear or?
Sir, sometimes the voice is breaking due to, I think, bad connection.
I don't know. Is it so? The weather is not good, that is okay, but should I use a different device or different? Okay. So let's go for a different thing. Just wait. Let me make some other arrangement. Am I audible now?
Yes, sir.
Is the screen visible?
Yes, sir.
Is it more clear than before my audio? My voice?
Yes, now it's okay. Now it's okay.
Okay, so have you understood this point which I have discussed just now? So that means how we are getting the frequency equals to P by 2 into revolution per second, RPS. Have you understood this point? So in the
Yes,
last
sir.
class, we discussed this. The electrical angle equals to P by 2 into mechanical angle. And if the electrical angle is 360 degree, will be equals to the P by 2 into 360 mechanical. So 360 electrical is nothing but we call it one cycle, one complete cycle. And 360 mechanical angle we mean by that is one complete revolution. Okay, and 1 cycles per second, that means if we divide both sides by second, then we will get 1 cycles per second equals to P by 2 into 1 revolution per second. So cycles per second is nothing but hertz. That is the older unit of frequency, cycles per second. Though the newer units of frequency is hertz. One more chat. Okay, so somebody saying that yesterday I denoted electrical angle by gamma. So electrical angle I can denote by anything. That doesn't mean. Okay, so gamma we used for not for electrical angle. The gamma we used for the angular slot pitch. Remember, angular slot pitch. We have used the gamma for angular, a specific notation for angular slot pitch. Okay. So electrical angle can be anything. It can be theta, alpha, anything it can be. It's an angle. Okay, so another form of this expression also we write just a minute, one more chat. Okay. So this n also we can write n by 60. Small n is in revolution per second, where the capital N generally we represent in revolution per minute. This is more popular unit of mechanical rotation or speed. So this RPM, how much RPM? So in that it will be N by 120. Okay, so that means the speed is 120 F by P. So you will require this expression for other machines. Okay, is that clear? Now you just tell me that the DC motor or any DC machine, as we discussed in the last class, that the armature which is rotating should be made of silicon steel, or rather laminated silicon steel. Why it should be made of laminated silicon steel? Why not normal cast steel?
Sir, because it will reduce the loss due to hysteresis. Because sir, in the armature there is continuous magnetization and demagnetization. So sir, if it is made of solid cast iron, then the loss by hysteresis will be more, and also the eddy current will be more. But if it is made of
Correct.
laminated steel, then it would be less. The loss would be less.
So that means the armature of a DC machine experience a reversal of magnetic field flux, isn't it? And can you tell me what is that frequency of that reversal? Okay, suppose the DC machine is rotating at a speed of 1000 rpm. Let's say 1000 rpm. Okay, so suppose the DC machine is rotating at 1000 rpm. So in which frequency the armature core of the DC machine will experience the magnetic reversal? What will be the magnetic reversal frequency? Do you know that? Generally, both this, you were saying this eddy current loss and hysteresis loss, both these losses are function of frequency. Both depends on the frequency. But if we want to relate this this eddy current loss and hysteresis loss for DC machine, then we should know that how we are getting this frequency. What is the frequency of magnetic reversal? Can you find out that? What is the frequency of magnetic reversal? If the DC machine is rotating at 1000 rpm,
Sir, from the equation F equals to Pn by 120.
correct. So what is that?
Number of poles is not.
Pole is not given. So you should have the number of poles. Suppose the number of pole is 6. Okay, if the number of pole is 6, then so 6
50 hertz.
1000 by 120. So it will be 50 hertz. Then the magnetic reversal frequency will be 50 hertz. That means the eddy current loss will be proportional to this 50 hertz and hysteresis loss also. So therefore, generally we laminate the armature core because it experiences the reversal of magnetic flux. Now what about
Sir, you told that the eddy current and hysteresis loss is proportional to frequency, but are they actually proportional to frequency? Because in the expression there was some f squared, then in the hysteresis loss this was f to the power x, this whole were
not
there.
proportional. I just told you that it's a function of frequency, not proportional.
Yes.
Sometimes it is squared, sometimes it is 1 by x. X is a Steinmetz constant. So different factors are there.
Yes, sir.
And sometimes if we can keep the flux density constant, then it may not be proportional to the frequency. It is not a function of frequency at all. In some cases, if the voltage
Yes.
is absolutely constant, it can be independent of frequency. So that is different issue.
Yes,
But anyway, generally what we take, the eddy current hysteresis loss are the function of frequencies. Okay. Now therefore we make the laminated, we make the armature core out of laminated silicon steel, but we don't make the yoke by the laminated sheet. Why? Because the yoke,
So the flux in the yoke is constant. It is not varying. So we don't need to
flux
laminate.
in the yoke is not a varying
Varying
flux,
flux.
time varying flux. Rather, it is not a time
Yes,
varying.
sir. Yes. Time varying flux. So we don't need to laminate it
Any.
because that constant magnetization, demagnetization does not take.
Yes. So that means there is no change in flux. There is a flow of flux because yoke is the important part of the machine through which magnetic flux completes its path. So that means through yoke the magnetic flux flows. But that magnetic flux which flows through the yoke is not time varying in nature. So therefore we don't need any lamination in the yoke. So this is very clear. So for armature we need lamination, for yoke we don't need lamination. What about the magnetic poles, field poles? Do we need laminations there? Okay, so for poles
Sir,
also,
please repeat the question, sir. Sir, please repeat the question.
for poles, north pole, south poles, that means the field poles. Field poles which are static.
Sir, the magnetic circuit, sir, the path completes, it starts through the, মানে এটা যোগ দিয়ে যায় আর পোল দিয়ে নিজে সার্কিটটা টোটালটা কমপ্লিট করে, তাহলে ওটা তো পোলের মধ্যেও যেটা যাচ্ছে সেটা তো টাইম ভ্যারিং নয়, তাহলে ওখানে তো ল্যামিনেশন দরকার লাগবে না?
Correct. So that means as the poles is also static in nature like your, that means the flux which flows through it is not a time varying in nature. So that means poles should be, or poles may be made of non-laminated steels, iron. But the problem with the pole shoes, as you have seen that if this pole is like this, it is extended at the end, which is called the pole shoe. So this is the yoke, this is the yoke portion, this is called the pole body or pole core, and this is called the pole shoe. And here your armature is there like this. Okay, and you have armature coils in that. So I have drawn only that part. These pole shoes should be laminated. Why? Because
So the flux flowing through the armature may pass through the pole shoe because it is.
okay, so I'm just discussing that. You see, flux generally tries to flow through the minimum reluctance path. You see, where you have the coil, there this distance is much larger compared to the teeth. So these are called teeth, and these are called slot. Okay, so conductors passes through the slot and the extended portion of the armature pole is called the tooth. Okay, and this tooth plus slot, this is called one slot pitch. Okay, so flux generally flows through the tooth because it gets a minimum reluctance path through it. Okay, now here the pole is fixed. When this portion is rotating, then what happens? When this tooth leaves this portion, so there will be a sudden change in the magnetic flux in this portion. Okay, so there are several portions in the pole shoes where you have this type of flux change due to the flux swinging. So this phenomena is called the flux swinging. Flux swinging phenomena. That means here the, if we draw it here, you see the flux distribution is more, but here it is less, here it is more, here it is less, like this. Isn't it? So different portion of the pole shoes experience different different flux densities. So due to this change in flux densities or flux, the pole shoes are generally laminated because eddy current losses would be there. Pole shoes are laminated, and sometimes it is not possible to differentiate the pole core and pole shoes. It is an integrated thing. So then the pole cores are also laminated. Okay, so have you understood this point? এই পয়েন্ট বুঝতে পেরেছো?
স্যার এই ফ্লাক্স সুইঙ্গিং এর কেসটা ঠিক বুঝলাম না।
বুঝলে না?
হ্যাঁ স্যার এই জায়গাটা একটু বুঝতে অসুবিধা হচ্ছে।
হ্যাঁ
হ্যাঁ স্যার এই জায়গাটা আরেকবার একটু রিপিট করুন।
হ্যাঁ, okay, so this is actually there is a change in the flux density, so in the pole. Okay, দেখো আমি যে পজিশনটা এঁকেছি আর্মেচারের, এখানে ফ্লাক্স ডেন্সিটি যদি আমাকে ড্র করতে হয়, কিরকম ভাবে ড্র করতে হবে না, এই যে একদম এই কানার পোরশনটা একটু বেশি, এখানে একটু বেশি, যেখানে স্লট আছে কম, আবার এখানে টুথ আছে এখানে বেশি, এখানে কম, আর যেখানে 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 টুথ আছে সেখানে ফ্লাক্স ডেন্সিটি বেশি। কিন্তু এই নেচারটা তো সেম থাকছে না। যখন আর্মেচারটা ঘুরে যাচ্ছে, ধরো এখানে এখানে এই স্লটটা এখানে চলে এলো, তখন তো এখানে আবার ফ্লাক্স ডেন্সিটিটা কমে যাবে, এখানে বেড়ে যাবে। বুঝতে পেরেছো? বুঝতে পারছো না? হ্যাঁ
হ্যাঁ পারছি, এবার পারছি।
হ্যাঁ, মানে যেখানে যেখানে টুথ থাকছে সেখানে তোমার ফ্লাক্স ডেন্সিটিটা বেশি হচ্ছে পোল শুতে, অন্যান্য জায়গায়। হ্যাঁ, এবার বডি দিয়ে যখন আসছে তখন তো সব একসাথে আসছে, কিন্তু যখন পোল শুতে গিয়ে ডিস্ট্রিবিউটেড হচ্ছে তখন কিন্তু সমানভাবে ডিস্ট্রিবিউটেড হচ্ছে না। যেখানে যেখানে টুথ আছে, wherever they are getting the teeth, there the flux density becomes more, where they are getting the slot the flux density becomes less. So that means there is a special distribution of flux density in the pole shoe, but this special distribution, if it would fixed, then there is no question. But this special distribution is also not fixed in time, because with this armature rotation this special distribution also changes. So therefore the magnetic flux reversal will come. And that frequency is not the frequency of the magnetic flux reversal in the armature core. That is much higher frequency. বুঝতে পারছো? এখানে যে ফ্রিকোয়েন্সিটা হবে এখানে কিন্তু ফ্রিকোয়েন্সিটা বেশি হবে অনেক। বলো। বলো, শুনতে পাচ্ছি জয়। ওকে,
আমি কিছু বলিনি।
আচ্ছা, আর কেউ? ঠিক আছে, বোঝা গেল why the pole shoes are generally laminated. The machine which you have, I think some of the groups have already completed the lab of study of AC and DC machine in first year. Those have seen that in our machine which is there in the machine lab. Okay, so that is also having the laminated pole core and pole shoe. Generally very small machines, in small DC machines, the pole core and pole shoes are also laminated because they are the integral part. Okay, so this point I wanted to mention regarding this construction, and if I have one more thing I will discuss in later stage. Now let me show you the symbol for a DC machine. So this is the symbol of the armature. So I told you that there are two coils, armature coil and field coil. Armature coil which carries the actual current, and field coil which is used inside the machine to provide the magnetic flux. Okay, so that is this. So this is called the field coil. So field coil is denoted by a coil, but armature coil is denoted by a circle with two brushes. If there are more than two brushes also, the symbol will remain same. So armatures are also the circle with two brushes. ওকে, এরকম হবে না যে যদি 6টা ব্রাশ থাকে, মানে ল্যাপ ওয়াইন্ডিং 6 পোল ল্যাপ ওয়াইন্ডিং এ 6টা ব্রাশ দরকার হয়, যদি 6টা ব্রাশ থাকে I will draw 6 brushes, not like that. So always I will draw only two brushes for the symbol of the DC machine. So this is the symbol of the armature, armature coil, and this is the symbol of the field coil. Okay, now how can I get the voltage induced in this armature? If I have a current in the field, isn't it? Otherwise it will not be a magnet. So two things we need. We have to flow the current through it. How can I flow the current through it? By applying a voltage across the field. So VF is the voltage across the field, which will flow some current through the field coil. Then it will generate some flux phi. Okay, what we need some rotation. Okay, we need some rotation, that is N, because without the rotation, without the mechanical power, it will not generate any electrical power. So this phi into N we need, and some constant there in the inside the DC machine, that is ZA by A. So then we'll get the voltage induced EA. So we'll get the voltage induced EA across it. Okay, so these are the constants. So Z is called the total number of armature conductor, and A is called the parallel paths for parallel circuits, and P is the number of pole. So this comes basically from construction of the machine. Okay, and these are the variables. So construction থেকে যেটা আসছে constant, these are called the parameters, and these are the variables যেগুলো vary করতে পারে. The parameters cannot vary or should not vary, because number of pole cannot be changed once the machine is already complete. The number of poles cannot be changed, number of parallel circuits cannot be changed, number of armature conductor cannot be changed. So they are the constant parameters inside the machine. The thing which can change is the flux, and so it's very simple that who will generate the flux. If there are number of turns, we should say some TF, otherwise we will be confused with the RPM. So if TF is the number of turns in the field coil, and if IF is the field current, then this is the MMF of the field MMF. Field MMF will be TF into IF. For transformer you use N for this number of turns, but here we should use T in number of turns, because we have already used N for the revolution per minute. So this is the field MMF, and the flux is the MMF by
Sir, here N is per minute or revolution per second.
N, capital N is revolution per minute, RPM, and small s N is RPS. Capital N
Okay,
is revolution per minute, the speed in revolution per minute, RPM, যেটা আমরা মোস্টলি ইউজ করে থাকি, and small n যেটা এক্সপ্রেশনে আছে সেটা হচ্ছে RPS. মানে এখানে তুমি যদি আর n ক্যাপিটাল n আনতে চাও, you have to write down n by 60. If you want to replace this, you will get n by 60. Okay.
Okay, sir. Okay.
Okay. Now, so this is the basic notation of a DC machine. I think you have understood this point, and we can vary this voltage by two things. We have, so that means we have speed and we have flux. If we vary the speed, the voltage will vary. If we vary the flux, the voltage will vary. So that means here we have two independent variable, flux and speed, and we have two only one dependent variable, that is induced voltage. Is that clear? Now here the configuration we have drawn is we are exciting the field coil by another voltage source, VF, isn't it? Can you see this? We are flowing the current through the field coil by another voltage source. So that means we want to generate a voltage source. For that we need another voltage source. মানে একটা ডিসি ভোল্টেজ আমি জেনারেট করতে চাইছি, তার জন্য আরেকটা ডিসি ভোল্টেজ আমার লাগবে। Are you getting? So this type of configuration is called the separately excited. Here the field coil or the field winding is excited separately. Now you'll ask me that what is the another arrangement? Can you tell me what is that? What can be another arrangement?
Well, so, sir, we can connect the field to the EA. That means the induced voltage can itself excite the field coil, sir.
Correct. So that means we are getting some voltage, isn't it? The EA voltage we are generating. Why not the same voltage can be induced for the field coil? So that means if we don't use any external voltage source or separate voltage source. If we just connect field coil to this, that will serve our purpose. Okay, so that means he's saying that if I have this type of connection where the voltage which we are getting induced in the armature, why not the same voltage can be used for exciting the field coil? So that means in that connection, what we'll do, we'll short A1, F1 and A2, F2. Then this armature will flow the current through the, sorry, if there is no current here, but this armature will flow the current through field. Are you getting? So this type of configuration is called the self-excited. But there are other self-excited configuration, but this is one of the self-excited configurations. So self-excited. So have you understood these 2 points? So one is called the separately excited, where the field coil or field winding is excited by a different voltage source, by additional voltage source. You should have 2 different voltage source. Sorry, one you will generate. But here for the separately excited, the thing is, the advantage is, suppose your voltage, your machine is a 440 volt machine, but your field coil is only 110 volt, designed for 110 volt. Because if we can design the field coil for less voltage, then the insulation of the coil required will be less. Okay, so the design of 440 volt coils and 110 volt coils are completely different. So if we can design the field coil for lesser voltage, the insulation requirement of the field coil will be less. Okay, so suppose if we have this kind of thing, the armature is designed for 440 volt and the field coil is designed for 110 volts, then we have to go for this separately excited mode, because in that case this 110 volt coil cannot be connected across the 440 volt coil. Then the insulation of the 110 volt coil will be punctured. Okay, so that is the thing. If both the coil, both the armature coil and
Sir,
field
please
coil,
repeat the last part.
I am saying that if we have armature coil and field coil which are designed for different voltages, armature coils, for an example, if the armature coil is designed for 440 volts and the field coil is designed for 110 volts, in that case we have to go for the separately excited mode, because in that case if we connect the 110 volts across parallel across the 440 volt, then this 110 volt coil will be punctured, its insulation will be damaged. Is that clear? At 440 volts. So that is a practical
Sir, we can
problem.
use voltage divider.
হ্যাঁ, সে তুমি অনেক কিছু ইউজ করতে পারো, তো যত ইউজ করো তত তো খরচ বেড়ে যাবে। আমি বললাম সিম্পলি এইভাবে করা যাবে না, সে তুমি ভোল্টেজ ডিভাইড করে করবে না কি করে করবে, সেটা তো জুগারের ব্যাপার, জুগার লাগবে, রেডিমেড পারবে না তুমি করতে, সেটা রেকমেন্ডেড না। তুমি যদি রিওস্ট্যাট দিয়ে লাগাও, তার মধ্যে দিয়ে কারেন্ট ফ্লো করবে, রিওস্ট্যাটের লস হবে, তুমি কেন পাওয়ার লস করবে শুধু শুধু? Field is basically a coil. Coil is basically an inductive element. It consumes very less power. And if you use some resistance divider, potential divider, or rheostat kind of thing, it will consume huge amount of power. Okay. So how much time we have? So this is one self-excited. Today only I am just discussing this simple thing. Otherwise, I don't have time because it is already 2:40. From the next class, we'll start with the other part of the constructions, like armature binding, commutation, armature reaction, etc. That we need another for each topic we need 2 to 3 hours. So therefore I am just discussing these basic things for you. So another configuration which is possible is that this field coil, if we connect in series, so another possibility is there. In that case, the armature coil and field coil will be connected in series. Okay. But here the problem is there should be some load, otherwise the field will not be active. Here we should have the load. Here it can run without load. Here it cannot be run without load. Only with load it can function properly, because here all these currents are in series. That means the load current, field current, armature current all will be the same, because they are all these components are series. I will discuss all these later, but only for this general discussion. And another thing is which we will require is that the voltage. Actually here only this without load, everywhere we have not considered any load. Now if we see in case of separately excited configuration, if we connect the load there, which will require some current of IL. Do you know what is load? Do you know? তোমরা জানো লোড মানে কি? যেটা পরীক্ষার আগে
Sir,
তোমার
anything
পড়ে। বলো,
sir,
anything?
anything resistance, inductor, any kind of electrical equipment, suppose any from simple resistor to inductor, in capacitor, or any type of electrical equipment like fan or light, they all are loads actually.
Passive components.
হ্যাঁ কি শুনতে পেলাম না।
Passive components.
কি
Sir,
acid?
any component which can provide, sir, any component which can provide an impedance.
Sure, আর?
Means it can be a resistor. In that case, it will be resistance. Inductor, inductance, means it will give an impedance.
It will give an impedance.
Here it can be mechanical. So here it can be mechanical load.
No, I'm asking the electrical load only. I'm asking just electrical load. What is
Some
the
electrical component that creates some voltage drop.
Is it written in the book?
I don't know, sir. আমি এটা নিজে থেকেই
So it
বললাম।
can be passive components. Will it be?
Okay, so Obirup Sarkar is written. Okay, so I've just missed that. Obirup Sarkar, can you unmute? Obirup Sarkar? poor connections. Okay, so he is writing one thing, that load consumes electrical power, but he can't unmute himself because of the poor connection, poor connectivity. Okay, so that is the right definition of, as written in the books mostly, that the load is something which consumes electrical power. Is that clear? That means load is something, as per the book, electrical literatures, the load is something which consumes the power. So that means if you have a resistor, it consumes power. If you have a fan, it consumes power. If we have immersion heater, it will consume some power. If we have refrigerator, it will consume some electrical power, which consumes some electrical power. And electrical power, the definition of electrical power, you know, we have studied in details in Shivaji sir's class. What is the different part of the powers: apparent power, reactive power, active power. So here we are dealing only with the electrical power, which consumes the electrical power. Nirmala Nandi is writing that the load is an electrical component which is connected across the circuit as per the requirement to calculate power consumption or to calculate current or voltage across 2 points in the circuit. This is a very long definition. Okay, the thing is the same. So that means which consumes some electrical power. Okay, বুঝতে পারছো? এটাই হচ্ছে লোডের ডেফিনিশন। In our household supply, we have generally single phase power supply. So that means we have 220 volt or 230 volt, 50 hertz. Okay, and we have one live wire and one neutral wire. The live wire sometimes we also call the phase wire, the phase and neutral. So these two lines are coming from the utility or the supply, either ACDCL or CSC, the live and neutral. Okay, then how our connections are made for our household? In the live we have some switch. Okay, and then from the switch we have some load, that means the lamp. Then from the lamp the neutral is connected. So that means the lamp and the switch is connected in series. Are you getting? So this is your load, one of the load. So suppose this is a lamp, and this is the switch. তো বাড়িতে যদি কোনোদিন কানেকশন করতে হয়, সবসময় মাথায় রাখবে the switch will be connected. So one terminal will come in the switch from the live directly, and another terminal of the switch will go to the load directly, and in the load one terminal should come from the neutral. In the load one terminal come from the neutral, another terminal come from the switch. So this is how the connections are made. So this is one switch, so another switch, so another load will be there. Suppose that is a fan. Okay, so here also it is like this series. So this is how we have different load in our household, and we all these loads are connected how? In parallel. Can you tell me why? All these loads are connected in parallel. So এরকম আমরা সুইচ বাড়াতে বাড়াতে যাব, আর আমার ডিভাইস গুলো প্যারালালে কানেক্ট হতে হতে যাবে। Can you tell me why they are connected?
So that the voltage.
Okay, so that the voltage across each.
So that the voltage drop, voltage yes.
Drop নয়, voltage. Voltage drop তো পরে হবে। The voltage we can apply across any load can be constant, and constant রাখারও কি প্রয়োজন, because that can create some standard. Then all the supplier will design for the same voltage and frequency. বুঝতে পেরেছো? এবার এটা যদি হতো যে কারো 30 ভোল্ট লাগছে, কারো 20 ভোল্ট লাগছে, কারো 50 ভোল্ট, কারো 220 ভোল্ট, কারো 110 ভোল্ট, তো সাপ্লায়াররা পাগল হয়ে যাবে ডিজাইন করতে করতে। If we can fix our voltage at 220 or 230 volts, then suppliers will be happy. Then they will design for a particular voltage. Okay, so if we connect all the loads in parallel, then all these devices are designed for a particular voltage, suppose 220 or 230. Okay, so that is all these loads are connected in parallel. Okay, now আমি যে কারণে এটা বলতে চাইছি সেটা হচ্ছে, so that means when we are switching on, বলো বলো আমি শুনছি।
স্যার
Anything?
লোডের যে ডেফিনেশনটা আপনি বললেন, যে 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 কোনো কিছু যেটা পাওয়ার টানে ইলেকট্রিক্যাল পাওয়ার কনজিউম করে সেটাই হচ্ছে লোড। তো স্যার আমি বলেছিলাম যে যার এই ইম্পিডেন্স আছে সেই হচ্ছে লোড। তো কোনো ডিভাইস কি এমনি হতে পারে যে পাওয়ার টানছে কিন্তু ইম্পিডেন্স নেই? ইম্পিডেন্স তো থাকতে হবে সে যদি পাওয়ার টানছে।
হ্যাঁ, কিন্তু ব্যাপারটা কি বলতো, ব্যাপারটা হচ্ছে মানে আমরা জেনারেলি এটা বলি, তোমার ব্যাপারটা ইনভার্সলি প্রপোর্শনাল হয়ে যাচ্ছে ব্যাপারটা, বুঝতে পারছো? যে যত পাওয়ার টানছে সে তত লোড বেশি। ইম্পিডেন্সের ব্যাপারটা ঠিক উল্টো, যার ইম্পিডেন্স বেশি তার লোড কম, এরকম ব্যাপারের মানে ঠিক ইম্পিডেন্সের সাথে ডাইরেক্ট রিলেটেড নয়। আমি আসছি একটু পরে।
আচ্ছা আচ্ছা, ওকে ওকে স্যার, ওকে
বুঝতে পেরেছো? সেটা আমি আসছি একটু পরে।
হ্যাঁ স্যার বুঝছি, ওকে ওকে।
Now you see, suppose I have a lamp, so you should have the concept of the load very clear as an electrical engineer, because this should be clear from the first year itself. Otherwise, you will have lots of problem in due course. Suppose you have a lamp. Okay, so generally আমরা কত 50 ওয়াট ধরো, 50 ওয়াট ল্যাম্প, 60 ওয়াট ফ্যান, আর একটা ধরো 40 ওয়াট বা 20 ওয়াট ধরো সিএফএল ল্যাম্প 20 ওয়াট। সো এরকম আমরা লোড কানেক্ট করতে করতে যাচ্ছি। So what will happen when we switch on the first load, which is 50 watt lamp? What will happen? Before that, before connecting any load, how much current is flowing through this line? No current. So initially current was 0. Right? When we'll switch on this 50 watt lamp, how much current will flow? 50 divided by 230. So how much it is? Let me
0.217.
0.217. Correct. Point, only fraction of current, 0.174, suppose. Okay, now next, already this is switch on, another load I am switched on, that is a 60 watt fan. What will be the current now? So this all will already this will be there, isn't it? Because they are connected in parallel, so more current will flow. So that means 60 plus 230. 60 by 230. So how much it is? 0.261.
Yes.
So 0.2174 plus 0.261. still it is less than 5 ampere or even 1 ampere. Okay, so this is how, if we go on switching one by one load, which we are calling load, actually what is getting increased?
The total current drawn from the source.
Current. So that means the total current drawn from the supply. That means the current is getting increased. Okay.
But sir,
So,
actually power
bolo?
actually power drawn টা বাড়ছে, ভোল্টেজটা কনস্ট্যান্ট থাকছে, তাই কারেন্টটা বেড়ে যাচ্ছে।
কারেন্টটা বাড়ছে, কারেক্ট, তাই কারেন্টটা বাড়ছে। As the voltage drop for our most of the applications are constant, so for us the load is nothing but current. So now on we'll use the current as load. Okay, so if the load is increased, power consumed will be increased, actually the current will increase. So load is nothing but the current, not the impedance. So here we are connecting some load, means we are connecting some current. Forget about the impedance it has. Okay, because when you will connect the load, you are fixing the current. So therefore, if we have seen the load box we have in our machine lab, in all the switch we have the current rating, not the impedance rating. Have you seen the load box in our machine lab? Okay, so if you see,
Yes.
there are 1 ampere, 2 ampere, 5 ampere, these current ratings are there. Okay, not impedance, no voltage, no power, only the current ratings are there. So for us, for constant voltage application, load is nothing but the current. Okay, so when we'll change the current, we are changing the load. So that means load is interpreted as the current for constant voltage application. Okay, so that means when we'll connect the load in case of separately excited, so field current or the armature current will not get ampere, the field current will not get ampere by the load. Okay, for separately excited, because the field circuit and armature circuit is completely different. Here the field circuit, for separately excited, the field circuit and armature circuit is completely different. So that means the field current is no way will be hampered by the load current. Okay, but that is not the case for self-excited machines. Today we don't have much time, so therefore I won't discuss that. But the thing we should write here, that the voltage which we are getting when the machine was at no load, and the voltage which we are getting at the terminal, so that two voltages are not same. Are you getting? Suppose when the load current was 0, which is called a no load condition, what is the expected voltage across the terminal? That is the induced voltage EA, the same voltage which we are getting by this expression. Okay, so that means we will get this voltage across the terminal only in case of load current is 0, but for other loads will not get terminal voltage as EA, because for other load current there will be a voltage drop inside the machine itself. Just like in a battery, if you draw some current, due to the internal resistance drop, there will be less in voltage at the terminal. So therefore here also we'll get a different voltage VT. The terminal voltage will be different for other values of load current. Are you getting? So this you should remember. So that means this is the voltage expression for DC generator. And sometimes we also consider a voltage drop across the brush, because brush being a semiconductor type material, the voltage across the brush is almost fixed to 2 volt. So this is more general expression for DC generator. And for DC motor, the same expression is valid with positive sign. So this is for generator and this is for motor. Now, if you have any question, you can ask.
স্যার
স্যার ওখানে 2 ভোল্টটা কেন লিখলেন?
Due to the brush, because brush, the material of the brush is carbon.
স্যার
The material of the brush is made of electrographite. Brushes are made of graphite. So graphite is a form of carbon. Carbon comes in the period of the semiconductor materials. So that means carbon behaves like a semiconductor material. So that means the voltage drop across this brush doesn't change with current. See, it almost fixed at 2 volts. Okay, so that means if you don't understand this point, so then you can draw it
এটা তার
like
মানে এক্সপেরিমেন্টাল ভ্যালু। স্যার 2 ভোল্ট তার মানে এক্সপেরিমেন্টাল ভ্যালু।
হ্যাঁ 2 ভোল্ট এক্সপেরিমেন্টাল ভ্যালু। সবই তো
ওকে স্যার।
ভ্যালু মানে এক্সপেরিমেন্টাল, মানে তুমি এক্সপেরিমেন্ট না করে ভ্যালু মেজার না করে ভ্যালু কোথা দিয়ে পাবে? So that means it is like this. Suppose this is has RA and this is your EA, and here 1 volt you can say, here you have 1 volt. Not exactly, but you can write like this if you try to understand. মানে আমি ব্যাপারটা এরকম হয় না, কিন্তু যদি তুমি বুঝতে চাও, you can draw like this, and if some current flows through it, IA, then at the terminal you will get this VT, where VT can be written as EA minus IARA minus 2. Okay. Circle it like this. Any other question if you have, you can ask me, because we've already completed the time. Any question? Some fundamental thing you should not forget throughout your engineering career, like this load, definition of load, and the other things, the fundamental things you should not forget. Okay, if you don't have any more questions, so let me, okay, now, so let me take the attendance, then I will pack up for today's class. Give me some time. can stop sharing.